Collision theory. Today's lesson, we're going to look at how you describe the effects of the changes in certain conditions on the rate of reaction. So we're going to look at the effect of changing surface area, concentration, pressure, temperature, and catalyst on the rate of reaction, and we're going to explain it. So in an exam, you often get describe and explain the trend shown in the graph. So you first need to describe it by saying, as you increase the surface area, the rate of reaction increases. That is the describe part. Because then that is the explain. So that's the thing we're covering today. So let us look at surface area. If you imagine one big block, which are those green circles, then the hydrogen ions, which are the red ones, can only really hit it on the four sides. Now, if you take the same atom, but you split it into smaller bits, look how many more of the atoms are accessible for the hydrogen atoms to hit. There's many more surfaces for it to hit. Another way to think of it is if you take a square, cut it into four, and then you get four squares. So the difference is that here you have only these places to collide, the four sides, but here you have all these sides that it can collide with. So you have increased the surface area to volume ratio. There's a higher frequency of successful collisions is going to be a magical phrase. So I call it FOSC. Frequency of successful, sorry about that. Successful. I call it the phrase that pays because it gets you 2 marks. You see, the collisions per second is what the frequency means. And then more successful collisions is the next bit. So a successful collision is one in the correct orientation with the correct energy, which must meet the minimum activation energy. So when you're looking for a reaction to occur, the correct particles need to collide as well. So you can't have 2 red ones colliding because the hydrogen ion can only react with the magnesium here, not with itself. So that's what we mean by successful collisions. The correct particles colliding at the correct orientation and the correct energy. So by increasing your surface area, by making something smaller, so you've got lump or powder, the powder will have the higher surface area and the faster rate of reaction. All you have to say is that there's a higher frequency of successful collisions. The shorthand of what you need to say, I'm going to summarize at the end, and I have a specific set of notes that you have access to, and you just need to say those points. I've taken those from experience of many past papers and mark schemes. Now, to illustrate surface area to volume ratio, let's have a go. So let's take, for example, a cube of size 2. The area of one phase will be 2 times 2. And because there's 6 faces in a cube, we're going to get 24 centimeters squared. Now, the volume for 2 centimeters each side will be 2 times 2 times 2. Length times width times height. That would make 8 centimeters cubed. So the SA to V, surface area to volume ratio, will be 24 over 8, which is 3 to 1. Now consider making that cube 10 times smaller. So you're going from 2 to 0.2. The new phase will be 0.04 in its area times 6 will give you 0.24. Okay, there's just a 0 missing here. But overall, it gives you 0.24. Okay, now consider the volume. 0.2 times 0.2 times 0.2 gives you 0.008, or 8 times 10 to the minus 3. Now, if you do your SA over V ratio, instead of getting 3 to 1, you've gone to 30 to 1. So we've discovered something interesting. Each time the side of a cube decreases by a factor of 10, its surface area to volume ratio will increase by a factor of 10. And you can use that fact. It's very useful. So if you divide something 100 times smaller, it will increase the surface area to volume ratio by 100 times. Okay, let us move on to the next factor, temperature. This is the famous one. Everybody loves this one since they're young. You do this. If you increase temperature, you increase the kinetic energy of the particles, so the particles move faster. Now that will increase the frequency of successful collisions, which will increase the rate of reaction. Okay, so just say high frequency of successful collisions. That's what I prefer. Now, there is one finer point, like a higher level thinking. So remember, activation energy is the minimum energy for reaction to occur. Now, if you increase temperature, you do not change the activation energy. What you do is you increase the average energy of the particles. So if you think about it, that means on average, more particles are likely to exceed the activation energy. It's a little bit like the average mark to pass and get into a school entrance exam is 70%. You suddenly give everybody a pill and makes them all smarter. You haven't changed the pass mark, but everybody's smarter, so more people can pass. So the way you would phrase that, again, it is in my other notes, but I'll write it here. A greater proportion of the particles have energy greater or equal to the activation energy. That results in a higher frequency of successful collisions. Okay, that normally would only get examined if they tell you some of these things and ask you, can you give any other reasons for why the rate increases? Otherwise, you just stick with more energy, move faster, higher frequency of successful collisions. Let us now consider concentration and pressure because they're very closely related. One is for solutions, one is for gases. So if we increase concentration, we keep the size of the container the same, but we add more particles. So that we have more particles in a given volume of space, which means particles are closer together, which increases the frequency of successful collisions. But you must say particles are closer together, or you can say there's more particles in the same volume of space. Now, if you're dealing with pressure, it is a little bit slightly different. So say you have here 3 particles. I'm now going to make the box smaller. This is going to be a low pressure, and this is going to be a high pressure. So this time you would say the same particles or the same number of particles are in a smaller volume of space, which means particles are closer together and there's a higher frequency of successful collisions. So you only need to change the first part. Instead of saying more particles, you would say same particles in a smaller volume. Alternatively, you can just say particles are closer together, but this is better. Okay, so these will be in the summary notes. And the last one is now catalyst, which we must talk about. Before we start the catalyst, I'm just going to say one more time, activation energy is the minimum energy that the particles need to collide with in order to result in a reaction. So a catalyst does quite a few things. The famous phrase you have to say is it lowers the activation energy, 1 mark, by providing an alternate pathway, 2nd mark. Therefore, more particles have. Now, I don't like the way this essentially is phrased. I would say more particles have energy exceeding the lower activation energy. EA is how we represent it. Therefore, we have a higher frequency of successful collisions. Remember FOSC. A higher frequency of successful collisions. Collisions per second. Now, a catalyst also is unchanged at the end of a reaction, so theoretically you could filter it off. Now, we now need to consider the reaction pathway diagrams because so far we only did the energy level diagrams. And there is actually an error here. This should have pointed down. This is wrong. So I'm going to actually draw it out for you again in a better way. And we can put it in your notes. I just need a bit of free space. So 1 second, I'm going to get some white paper. And I will kind of sketch these out with you to show you. Make sure you have it correct. I mean, we did see it once before in the energy topic, but I'm going to just make sure I emphasize it here. So let me just plug in my device. And we're just going to sketch this out. Okay, so let's do exothermic first. So we're going to do exo. You sketch yourself a graph like this. You put your reactants here. Now energy is going to be released, so the products will have a lower energy here. You would physically put the actual reactants and products there. Then you draw a pathway like this. So the pathway includes what's called the activation energy, which is between the reactants and the top. This is called EA. Then you point an arrow downwards, because it's exothermic, downwards for your enthalpy change. The axis here will be the reaction pathway. And here you're going to just have energy. Now, if you were to use a catalyst, I'm going to change color. I can figure out the color. There it is, red. What you do is you lower the pathway, watch. You keep it exactly at the same point, finishing and starting. You draw an arrow up, always activation energy, and you call it EC. So that's the activation energy with a catalyst. So the pathway, the hill you have to jump over, has become smaller. And that, in essence, is what a catalyst does. So this time, imagine the pass mark used to be 70%. If you lower it to 60%, then more students can pass, because more of them have a greater mark than the average, because the average was lowered. So that means more particles have energy exceeding the activation energy, which means more successful collisions. Now the axes are going to be the same, energy. So this is endothermic. This was exothermic. Remember, hot, cold. Okay, reaction pathway or reaction coordinate you can put here. This time they absorb energy, so we're going to put the reactants down here. I'm going to put the products up here. Then I'm going to draw a big reaction pathway. Now, my activation energy is particularly important. It goes all the way to here from the reactants. Don't draw it from the products, that will be wrong. And the enthalpy change also points up because energy is being absorbed. Now, if you were to use a catalyst, we would lower this pathway. So we would start at the same point, go up and down. And this time our arrow will go all the way from here, but it'll finish lower down. So that's EC. Could I save this? I recommend you learn it well, because these will be easy marks in an exam. And now I'm going to rub this out, it's saved, and we're going to look at the summary of what you would say in an exam for each of the 5 factors. So I go to my common questions and answers notes, and we go to rates. It's a bit small, so I'm just going to enlarge each one. So these are the key points that get the mark. So what happens if you increase temperature? Make sure you always describe first, so you state the obvious. The rate increases. Particles gain kinetic energy and move faster. That's what you would add here. More particles have energy exceeding the activation energy, so there's a higher frequency of successful collisions. This one you don't have to put. What I would add, you can add it right now. Particles move faster. Okay, we might as well put that here as an extra one and save it. Right. What is the effect of increasing surface area? Rate increases because there's a higher probability of collisions because of the more faces. So there's an increased frequency of successful collisions. You can add the word successful. I would always put it. What's the effect of increasing concentration? Well, rate increases. More particles in the same volume of space means they're closer together, and as usual, increased frequency of successful collisions. Not sure why I didn't put successful here, always put it. Now for pressure, which was similar to concentration, the rate increases because we have the same particles in a smaller volume of space, they're closer together, and there's an increased frequency of successful collisions. And the last one that we just did was catalyst. So rate increases if a catalyst is used because the activation energy is lowered. There's an alternate pathway. And this is the extra kind of point. Greater proportion of particles have enough energy to react. So there's an increased frequency of successful collisions. Learn these really well by just covering them up and seeing if you can state it out loud and if you know all the points. That's the best way. With that, we have brought to an end the lesson on rate of reaction and kinetic theory. We've also done how to measure rates of reaction in the previous lesson. So next lesson, we have to look at graphs and how you sketch different graphs depending on the changing conditions. And then we'll have one fourth lesson on experiments and how you do the fair test and stuff like that. So tune in next time for the graphs lesson.